All right, good morning, everybody. Geometry, hopefully you guys have all turned in your homework, and we are going to go over the answers to this, okay? So, we have a quiz. No, not a quiz. We have a test coming up next week, and the test is going to be on Tuesday, but before that, we have a lab. So tomorrow we don't have class. On Friday is going to be, essentially the day to work on the lab, or today you can work on the lab, whatever. So on Friday, I'm going to assign you guys some review problems, and on Monday, we're going to go over the review problems. But in the meantime, I have already posted your lab. You guys have a lab to do that is essentially about this thing right here. So gas stoichiometry. So that's what your lab is all about. And it's a beautiful, beautiful, beautiful lab because it kind of combines a lot of the stuff that we've learned throughout the year. Okay, it's going to go all the way back to what we talked about in terms of unit conversions. It's going to be about molecules. It's going to be about chemical reactions, about solutions, and now about gases, and also about stoichiometry. So and even acid-base chemistry is in there too. So it's literally so much of what we have done this year all packed into one lab. And that's really what's beautiful about this lab. So this is what you guys are supposed to be working on over the next couple of days. You can do it today if you want to. You can do it Thursday if you want to. Whatever. The lab itself doesn't take a long time, but the calculations may take you some time. I'm going to help you out with the calculations, but in reality, the calculations are very, very, very similar to the calculations that we already went over for these sample problems. Okay? So, with that said, if there are any questions you guys have about anything, whether it's this material or the lab itself, feel free to ask. And make sure you check out the lab video, because I'm not going to repeat everything right now that's in the lab video, but I will mention some stuff. So, without further ado, let's jump right into the next couple questions. All right. And these next questions are real questions. They're real things that people use or people have done. And so this car airbags, these are real numbers, okay? So this is a real life situation. Obviously, somebody needed to calculate this stuff before they ever built a car airbag. And like, is this going to work, right? And so somebody needed to be able to do the chemistry in order to figure out how to make your car airbags. All right, so car airbags typically use this reaction. You might be wondering, well, why in the world do they use this reaction? And the main reason is, well, there's actually two main reasons. But the main reason is, first of all, this is fast. It's a very fast reaction that fills up the bag with gas, whereas a lot of other chemical reactions might not be this fast. And it's fast, well, check it out, because this is, of course, what kind of molecule? This is, well, what kind of reaction? This is one chemical going into two, so this is a decomposition reaction, right? So decomposition reactions are useful because they're fast. And this is not explosion fast, but it is very, very fast. Fast enough to fill up your airbag, between the time that you crash and you would actually, smack your head against something. Okay? So super fast because it's a decomposition reaction. The other reason that they use this reaction is because the gas produced is nitrogen, which is totally non-toxic, which is, something that you want, right? You don't want a bag filling up with carbon monoxide and then all of a sudden it pops and then shoot. Now you not only had a car accident, but you also have carbon monoxide all around you, right? You wouldn't want that, which a lot of decomposition explosive reactions would produce carbon monoxide, and you don't want that. Nitrogen is completely non-toxic, safe, which is the other reason why this reaction is used for car airbags. All right. So the first thing that we got to do for this reaction is balance it. We got 3 nitrogens here and 2 here. So of course, we're going to put a 2 there and a 3 there, giving us 6 and 6. Nitrogen is balanced. That now gives us 2 sodiums here. So we're going to put a 2 in front of here. Don't ever forget to balance your reaction. You must balance these reactions before you move on. Even if the test question doesn't tell you to balance it, make sure you balance it. Next, now we have typical airbag has a volume, so we have a volume, right? That's going to be our volume, 49 liters. Calculate the mass needed to fully inflate the airbag, and now we're going to assume a pressure and a temperature. So once again, we are going to use PV equals nRT. And what are we solving for? Where's the lab video? So Anna, the lab video, I gave you guys the link in Google Classroom. If you notice, so the link that you followed to come here to see this live stream, right below it, or not immediately below, but like 2 lines below it, is the link to the lab video, okay? Or you can search, right, you can, let me see, what is it called? I think it's called, so maybe Airbag Challenge. I think it's called something like that on my channel. Okay, so you might try Airbag Challenge with Ketzbook, and I think that'll show up too. But anyway, I gave you guys the link, and so you not only have the link, but you also have the safe link both on Google Classroom. So you should be able to follow that link. And if you can't see it, or if anybody's ever watching this at some other time, you guys can just search. It's my, one of my videos, and my daughter's in there too, and we're demonstrating the lab. Okay, Airbag Challenge. All right, so let's come back over here to number 4. We're going to solve for what? So PV equals nRT. We want to solve for N. And why do we want to solve for N? So that we can figure out from N the amount of the reactants. Okay, and that's the general procedure that we've been doing back in the sample problem I gave you, and also in the next problem, and also in the lab. So it's kind of the same general procedures. Okay, so we're going to solve for N using the ideal gas law. All right, so let's go ahead and rearrange it. We can solve for N by dividing both sides by RT. That's going to mean RT over RT cancel, and so N is PV over RT. We can plug in some numbers. P is, let me see, P is 1. Your V is 49 liters. Your R is always the same, 0.08206 liters atmospheres per mole Kelvin. And your T is, we said, assume 25 degrees Celsius. Now, obviously, you're nervous about the lab. Guys, obviously, the temperature is going to be different, right? In the wintertime or in the summertime, your temperature of your airbag is going to be different, which means that if you come into a crash in the summertime, your airbag is going to inflate more than it will inflate in the wintertime. So I don't know how they adjust for this in your car, because it could be a significant difference. But yeah, that's something to be considering. Make sure you have your air conditioning on in the summertime so your airbag doesn't inflate too much if you happen to be in a crash. But yeah, I don't know how, it probably won't make too big of a difference. Anyway, your temperature is going to be 25 degrees Celsius, but you must always convert that to Kelvin. So 25 plus 273 is 298 Kelvin. Okay? Let's go ahead and plug in the numbers to calculate N. So 1 times 49 is 49, divided by 0.08206, and divided by 298 is 2. Hey, that's so nice. These are real numbers, okay? For somehow, they have this particular airbag set up so that we have exactly 2 moles. Right, 2.00 moles of nitrogen, okay? Why do I know it's moles of nitrogen and not moles of sodium? Because sodium is a solid, nitrogen is a gas, right? So we have 2 moles of sodium gas, 2 moles of nitrogen gas that is produced in this reaction, or at least we need to have 2 moles of gas. So now we need to calculate the mass of our sodium. Well, so NaN3, you guys might not, I'm sure you're not familiar with the name of this. This is called sodium azide. It's not sodium nitride. Sodium nitride would be Na3N. This is NaN3. It's called sodium azide. It's a strange kind of polyatomic ion there, the N3 1 minus. Okay? Anyway, that's not important to actually solving this. Let's go ahead and do this. We have 2 moles of N2 that are produced by the reaction. And then we need to go back and say, okay, well, if this is N2 that we are producing, there's 3. This goes on the bottom. Why? Because I want to go from moles of nitrogen to moles of my reactant. I want to figure out how much reactant I need to make that much gas. So I'm going to put my 2 moles of nitrogen here, and I'm going to divide by 3N2 because I have 3 from the balanced reaction. And for every 3N2 produced, we use 2 NaN3. Okay? Last of all, we want to convert that amount from moles into grams. So we have 1 mole of sodium azide, and we're going to figure out how many grams that is. And in order to do that, we need to look on the periodic table to get the molar mass of our sodium azide. Okay? So let's check that out. That's going to be, the molar mass is 1 sodium. That's 22.99 plus 22.99 plus 3 nitrogens times 14.007. All right, so that gives you 65.011. 65.011 grams. All right, so this is the setup. Okay. Again, what are we doing? We're converting from moles of nitrogen to moles of sodium azide. Then we're going from moles of sodium azide to grams of sodium azide, and that's going to be our final answer. Okay? Going to be a 2-step conversion here. Let's do it. So it's going to be 2 times 2, right? So this 2 times this 2 divided by 3, and then times our previous answer, which was 65.011. And that's going to get us 86 point, so let's just say 86.7. 86.7 grams of NaN3. Boom, final answer. All right, question. So you got 2.000. 2.000. Oh, right. So you had, that should be, you're talking about for N? Sarah, you're talking about N, right? I think that's about right. And so let me just do that again. So it's 49 divided by 0.08206 divided by 298, and we got, right, 2.003. So I just rounded off to 3 significant figures, which is, you got exactly right. And so if you're interested in, let's see if that makes any difference here. So if we use 2.003 times 2 divided by 3 times 65.011, and we still get out, oh look, it did make a difference. Good job, Sarah. So that's a little bit of a rounding error, right? I rounded it to just 2, where it really is 2.003. Very good. So that's a little bit of a rounding error that I made over here. 86.7 I said, but it really should be 86.8. Good job, Sarah. It did make a little difference in our value for the final answer. Should be 86.8, and we should have used the number in our calculator, that 2.003, rather than simply 2 here. But, you know, there we go. Not a big difference. All right. So, any other questions on the front page? All right. Next page, let's go ahead and do that. Jacques Charles, I love this problem too. So both of these problems, I mean, these are some of my favorite problems you guys have throughout the whole year, right? Because these problems bring together all the different things that we've learned so far, right? Chemical reactions, acid-base stuff, solutions, now gases, and and stoichiometry all brought together. So it's just really, really beautiful. All right. So Jacques Charles, I also love this because this is a real thing. Remember, we talked about Charles's law before, and we said Jacques Charles was not just a scientist, he was also into extreme sports and all that kind of stuff. And so he was one of the very first, he was the first person to ever ride in a lighter than air balloon, and he was one of the very, very first people, or the second person ever to fly in some kind of vehicle. Okay, so Jacques Charles, his first hydrogen balloon was filled with, and these are real numbers, okay? I don't know exactly what it was, but it's approximately this, right? 380,000 liters of hydrogen gas. Who knows? It was probably not pure hydrogen gas because, of course, he wouldn't be able to make it totally, totally pure, right? He would lack that technology, but I'm sure a big part of this was hydrogen. For this problem, we're going to assume it was pure hydrogen. Okay, if Charles used the following reaction to generate the hydrogen, what volume of 4.5 molar hydrochloric acid did he need? What mass of iron did he need? So this is solving for two different reactants, but the first thing we do before we do anything is to balance the reaction. So we have two hydrogens here, we have one hydrogen here, so of course we put a 2 in front there. We have two chlorines here, and now we also have two chlorines here, so chlorine is balanced. One iron, iron is balanced, that's it. We just need that 1, 2, and we are totally balanced for the reaction. Next, we have a volume, we have a pressure, a temperature, so we need to calculate, once again, solve for N. Okay? That's going to be moles of gas. We have PV equals nRT, and so dividing both sides by RT, N equals PV over RT. Let's plug in some numbers. Pressure, we said here is 1 atm. The volume is enormous, right? 380,000 liters. We expect it to be big because it's a whole balloon. Like we're talking about the volume of a blimp here, right? R 0.08206 and T, we had 25 degrees Celsius, so convert that to Kelvin. 25 plus 273 is 298 K. Okay, let's plug in some numbers. That's going to be 380,000. You've got to make sure you have the right number of zeros here, right? So 380,000 divided by 0.08206 divided by 298 gives us 15,539. Now clearly that's too many significant figures, but we'll round it off at the end. Right, 15,539 moles. Now moles of what? This is moles of gas because this is the volume of that balloon that's filling up. But our gas is what? Our gas is hydrogen. So moles of H2. Okay? So what do we need to do now is a little bit of stoichiometry. We're going to take that 15,539 moles of hydrogen, and we want to figure out how much of each of these reactants that we need. So we're going to do this twice, two different stoichiometry problems. Okay, so we have our first part in this conversion is going to say, okay, we have one H2, and for every one H2 you make, you need one Fe. So this is 1 and 1. So that really does nothing for us. The number is still going to be the same. Next, we need to convert that into a mass. So we're going to say, okay, 1 mole of iron has a mass of, and you can get this directly off of the periodic table. right? So you look, iron is 55.845. 55.845 grams. And that means, and what I'm going to do right now, I'm going to store this number. So that previous number, that number of moles, I'm going to store that as X in my calculator because I'm going to need it again. So that means that we just take this number, that number of moles, we're going to multiply it times 55.845. And that's going to get me a very large number, right? 867,800 grams. And what I want to do is, because that's an unreasonable number to actually use, so 867,800 grams, I want to go ahead and convert that to kilograms. So I'm going to divide by 1,000. So that's essentially 868 kilograms of iron. And so that's a little bit more reasonable. So we have a little bit less than a ton of iron. 868 kilograms of iron. Okay? So we're halfway there. Well, actually, we're 2/3 of the way there. Now, the next thing we need to do is figure out, well, how much hydrochloric acid did he need? All right, so we got 15,539 moles of hydrogen. And our hydrochloric acid, so we say, okay, for every one H2 in the reaction, for every one H2, he needs 2 HCl. So you need to multiply by 2 there. Next, and this, let me see. We said, okay, next, notice that we have, what kind of hydrochloric acid did he use? Well, we don't know. I just made this number up. I just, totally made this number up. Anyway, so he used, or he could have used 4.5 molar hydrochloric acid. So this means this is 4.5 moles per liter. That means 1 liter has 4.5 moles in it. And we could go ahead and say, use the equation of molarity equals number of moles over the volume. But I find it easier to use this as our conversion factor, right? So we can say that, okay guys, sorry about that. Looks like we had a little connectivity issue there for a second. So we can say, we can use this in terms of our molarity equation, M equals N over V, but it's easier just to use our molarity as a conversion factor itself. So in your hydrochloric acid, 1 liter contains 4.5 moles. So this is a conversion between moles and volume. So what do we do down here? We start off with moles of H2, convert that to moles of HCl, and then what are we going to do? If this is moles here, we're going to put our 4.5 moles right there. And the bottom is 1 liter. And that's going to convert this to liters of hydrochloric acid. Okay? Let's go ahead and do that right now. So let's use our X. X was our 15,539 times 2 on top, divided by 4.5 on the bottom, gives us 6,906. Right? 6,906 liters of our hydrochloric acid. So that's a lot of this acid. Now, in all honesty, we really only have 2 significant figures for either of these. So this should really be, let's say, 870 kilograms of iron, and this should be 6,900 liters of hydrochloric acid. All right, and that combined together produces a lot of hydrogen, enough hydrogen to fill an entire blimp with hydrogen gas. So that is how they made hydrogen gas back in the day, back when Jacques Charles was making the very first lighter than air balloon. Super, super cool. At least I think it's super cool. So that's your homework. And your lab is very similar to this. Now, I bet you guys would like some extra hints. Now there's a few of you guys on here and some people might listen later, so let's go ahead and do our hints for the lab here at the end. Would anybody like some extra hints for the lab? Now maybe you haven't even watched the lab video, which is fine. And so this might not completely make sense to you in terms of what the hints are. But my honors class, I didn't give them any hints. I let them just figure it all out. But I'm going to give you guys some hints for the lab. If you guys would like some hints, I think you guys would like some hints. I don't care. I'm not even going to ask you. I already did, but nobody responded. I'm going to give you guys some hints anyway, whether you want them or not. So if you don't want hints, you can go ahead and log out and then come back in later when you actually realize that you need some hints. You know what? I'm going to go ahead and put it on this sheet, okay? And that's fine. You can just close out now and watch the lab video and then come back later and watch this and figure out your hints later if you want to, or you can just stay on here and listen to my hints. So in the lab, and I show you guys how to do it, the whole thing that you have to do on your own is do the calculations, right? In the lab, you're going to be doing what? You're going to react, what do we have? You have vinegar and you have baking soda. So baking soda is NaHCO3. This is sodium hydrogen carbonate, right? And you're going to react that with acetic acid. And acetic acid is HC, I don't want to mess this up. I think it's H2, so let me just draw it here. OH, yeah, so 2H3O2. So that's acetic acid, and the reaction is going to produce, interestingly enough, carbon dioxide gas plus liquid water, and you're going to get out sodium acetate, NaC2H3O2. And then this is going to be aqueous. Hello. This is going to be aqueous, and this is going to be a solid, and this is going to be aqueous. Okay, so that's your reaction. And so this is not easy or not hard at all to balance. You'll notice that if you try to balance it, well, actually it's already balanced, right? And so, well, it's, you'll notice that, okay, so we have the acetate here, balanced with that acetate. We have one sodium. We have two hydrogens here. So this hydrogen front and this hydrogen here. And you're going to be making, and then you have CO3. So you have, take away CO2, right? So you get one CO2, you're left with one oxygen and two hydrogens, so that makes water. So this reaction is already completely balanced. So that's the reaction that you guys are going to be using. Now, the trickiest, or one of the trickiest parts about this, at least for you guys, might be, well, how do I actually get the right numbers? Now, on the video that I showed you guys, I'm going to tell you guys, you know, how many grams are in 1 teaspoon. I believe it's about 5 grams of baking soda per teaspoon, okay? But the real question is, well, what about the acetic acid? What about the vinegar? Now, most of you guys are probably going to be using 5% vinegar. That is the most common. What kind of reaction is this? This is an acid-base reaction. That's probably the best way to describe this reaction, right? So here's your acid, your vinegar is your acetic acid, here's your base, and so it's an acid-base reaction. And you're getting out, sometimes your acid-base reactions, most of the time your acid-base reactions will produce water. Sometimes they also produce a gas like carbon dioxide or sulfur dioxide, but it really is an acid-base reaction. Okay. Now, the big question mark is, how much vinegar do you use? Now, you probably have 5% vinegar. If you have a different percentage of vinegar, then you can go ahead and adjust it appropriately. So, for example, you know, if you have 10% vinegar, you can change your, multiply the molarity that I'm about to calculate by 2, and you'll figure it out that way, okay? So most of you guys are probably gonna have 5% vinegar. You guys need to know, well, what is that? What is 5% vinegar? What's the molarity? Because all the problems I gave you guys have the concentration in molarity, not in percentages. So I'm going to go ahead and show you guys how can we convert a percent into a molarity. All right, so let's do that right now. All right, so 5%, what does that mean? That means that in 100 grams of this, you have 5 grams. So let's say if you have 100 grams of vinegar, that means you have 5 grams of acetic acid. That's what a percentage means. It means percent is per 100 of the total, 5 of it is the thing we're talking about, the acetic acid. Okay? But you know what? I don't want to use 100 grams. I want to use 1,000 grams. So in 1,000 grams of vinegar, I have 50 grams of acetic acid. Well, why do I want to use 1,000 grams of vinegar? Because although the density of vinegar is not exactly 1, I'm going to estimate it, because this is a pretty good estimation, that this 1,000 grams of vinegar is approximately equal to 1 liter. So that when I convert this into moles, then all of a sudden that number of moles is going to be per liter, and it will be equal to the molarity of the solution, which is what I want. So I have 5 grams of acetic acid and 100 grams of vinegar, which is 50 grams of acetic acid and 1,000 grams of vinegar, which 1,000 grams of vinegar is 1 liter. So all that remains is we now need to convert that 50 grams of acetic acid into moles. Let's do that now. Okay, so question. How do we know the percentage of the vinegar? You look on the label. It's got to say somewhere on the label. Unless somebody ripped off the label, it really should say on the vinegar somewhere, 5% acidity, 6% acidity. So if you want, you can just run, go and check right now in your kitchen. And if you have a different percentage, I can help you out. But it's probably going to be 5%. So make sure you look at the label. Look at the label. All right, let me get another color. All right, look at the vinegar label. All right, so let's do the math now. We have 50 grams of acetic acid, and what remains is we need to convert that to moles. So 50 grams, well, how do we do that? Well, of course, we want to convert it to moles, so we need to get the molar mass of vinegar. Well, what's the molar mass, not the molar mass, the molar mass of acetic acid. So we have the formula of your acetic acid, which is HC2H3O2, and so we're going to go ahead and do that right now. Let's see. We have 4 hydrogens, 1 here, 1 acidic hydrogen and 3 non-acidic hydrogens. So we're going to go ahead and just put them together here for our molar mass calculation. That's going to be 4 times 1.0079 plus we have 2 carbons. 2 carbons is going to be 2 times 12.011 plus we have 2 oxygens. So that's going to be 2 times 15.999. And that 60 is our molar mass. So let's go ahead and use that. So 60.05 grams is our molar mass. So this is going to be 50 divided by that number, 60, is 0.83. Okay? So that's going to be 0.83 moles. But we already said, so this is our number of moles. We already said that our volume's 1 liter, so our molarity is number of moles over volume. Volume's already 1, so that's going to be 0.83 divided by 1. So our molarity is, well, 0.83. Okay, and if you want it a little bit better, that's 0.833 moles per liter. So if you have 5% acetic acid, your molarity is 0.833. Okay, let's suppose you have 6%. Let's say your label says 6%. Well, all you do is you take this number, divide by 5, multiply by 6, and then boom. If you have 6% acetic acid, that's about 1 molar, or 0.999 molar. Okay, and you can do that with anything. Okay, so that is kind of the big hint that I'm going to give you guys, which I didn't give to my my honors chemistry folks. But do you guys have any more questions for me? And if you guys have any more questions, you can ask me on Friday, but I'm hoping that you'll figure out the lab before Friday. Definitely work on the lab before Friday, okay? So on Friday, I'm gonna give you guys a review guide for the test, and I will basically just be there to answer your questions, and that's it, all right? So we don't have there's no homework due Friday, all right? The lab is due on Monday, and the test is on Tuesday, but don't wait till the last minute to do those things, because if you wait till the last minute, you're gonna find that it's gonna take you a lot longer and you're gonna really mess up on something. Okay, so question. Oh wait, no, I already read that one. All right, so I think that's it. That's it. Do you guys have any more questions? Anything at all? All right, so I will see you guys on Friday. I think maybe we'll even do like a Zoom lesson instead. I don't know. Do you guys want to do Zoom or do you want to just stick with the YouTube? Zoom will let you guys ask your questions a little bit more easily. So we can do Zoom if you want to do that way. Or we could just stick with this because this allows me to answer questions more easily. So whatever you guys want on Friday. But we don't have anything due on Friday. So, please work on the lab. You should work on the lab because I know I'm going to give you guys extra time, but the whole thing is Zoom. So we'll do like a Zoom on Friday because nothing's due, and then we'll just talk. If you guys have any questions, I'll answer them, and if you don't have questions, then whatever. Or YouTube. It's 1-to-1 here. I don't know. Anybody else? You know what? There's limited people. So just email me and tell me what you guys would like, and say you guys want Zoom or YouTube. Again, Zoom makes it easier for you to. Nobody puts their pictures on Zoom anyway, right? And then it's just like you guys all see me, and I see a bunch of random pictures that you guys put, and I don't actually see you guys. So yeah, so we got 2-for-1s for Zoom. If anybody else would like YouTube, Zoo, that way we can actually talk. Right, so you can actually talk. It's just harder for me if I have anything math to do, it's harder for me to show you guys. But anyway, I guess we'll just do Zoom unless there's some more people. So it's 2-to-1. So we have like a total of 3 votes. Anybody else? I think Anna's there, and Anna probably doesn't care. She's be like, whatever, whatever. Either is fine. So Timothy's here too. Hi, Timothy. Timothy doesn't care, and maybe some other people don't care. Either way. So if anybody else really cares, you guys can vote by emailing me and tell me what you'd like. For right now, it's 2 votes for Zoom, 1 vote for YouTube, and I'll see you guys on Friday. Nothing due on Friday, but work on the lab before that, okay? Connor, it's going to be awesome. I know you're going to do a great job, Connor. All right, see you guys.